Let's next see the theory of permutations of distinct objects more seriously. Say we have n distinct objects and we want to arrange any r of them, where r is a positive integer less than or equal to n. Less than or equal to n, of course, because the number of objects available itself is n. The point here is that the objects are distinct, and in this part, repetition is not allowed. Actually, we have already seen how to do so, but now we are going to again see it more systematically. So you can imagine that we again have R boxes which are to be filled in using these n objects without repeating anything. The usual stuff which we have been doing. The first box, for example, can be filled in with any one of these n objects in n ways. So we write n here. Once you have made one such choice, the number of available objects to you now is n minus 1 because you cannot repeat. So that's why the second box can then be filled in n minus 1 ways using any one of the remaining n minus 1 objects. And that way it goes. Eventually you reach the rth box. You can see how these numbers are appearing in what pattern. Here you have n minus 0, n minus 1. Whatever you have here you have one more than that. So that means here it should be r minus 1. And then we take the product of the numbers. So this is the number of ways of arranging R objects from given n distinct objects without repetitions. And we give this number a name also so that we can write it more easily. NPR, P stands for permutations. But can we now manipulate this number to bring it into a compact form, more compact form than this one? What if we write the missing numbers here after this one? By missing numbers, I mean this. You see, every time we are writing something new, starting from this n, we are writing one less, right? For example, if n is 6, the next number is 5, then the next number is 4. Instead of stopping here itself, we continue until we get to 1. So what will be the number after this? That means you subtract 1 more. So here you are subtracting r minus 1 from n. You subtract 1 more means you subtract r from n. Then in the next number which will appear after this, you subtract r plus 1. So like that things are decreasing and eventually you reach 1. But to compensate for this extra part, you also divide by this. Now this is something that we can write very easily because of factorial that we have already seen. Because we have written all numbers here in the numerator, I mean if you look at it from this side, starting from 1 all the way up to n, so that is by definition n factorial. Similarly, the denominator is n minus r factorial. So you have got a very convenient formula for NPR in terms of factorials of n and involving n and r. Now after this in the text we have some examples and exercises involving the notion of factorials. Only just that, which are so easy that they are left to you as homework. Instead, what we are now going to do is we will go back to those initial examples and see how we can use this to solve those examples. Let's recall this example where we have been asked to find the number of 4-letter words with or without meaning that can be formed using the letters of the word rose without repetition of letters. And the required number is 4p4. Here n is 4, n is the number of objects available which are all distinct, which in this case are the letters of the word rose. They are all distinct objects. And we have to arrange them means taking all of them at a time. So all 4 of them. So that's why r is also 4 here, which we can take because r can be equal to n. R is only less than or equal to n, it can be equal to n. So by the formula, this is n factorial, that is 4 factorial divided by n minus r factorial. You already know that this value is 24. The denominator is 0 factorial. Don't be scared by having 0 in the denominator. We have factorial, okay, not just 0. And if you remember, when we discussed factorials, there we separately defined 0 factorial to be 1. So that we now use, and we have 24. So you go back to that example, you will see that this is the exact figure that we found there also, using those boxes and going through elementary argument. Our formula for NPR, that is this one, comes with this condition that R is positive and less than or equal to N. While we do understand that we need R to be less than or equal to N, it does not make sense to, for example, arrange 6 objects from a given set of 4 objects. Okay, that is a meaningless requirement. But what if we want to make R equal to 0? What should NP0 be? What should it even mean? It means that from the available n objects, you are not choosing anything. That means you are not really arranging anything. So that means in this situation, nothing really gets arranged, and that can happen in only one way, not more than one way, of course. So that's why this should be 1. But is the right hand side also 1? If you put R equal to 0, let's see. Yes, that is also 1. This one is 1 by what we said just now. And what about this one? If you put R equal to 0 here, then you get n factorial divided by n factorial. So that's again 1. And this just means that you can extend this formula slightly to include the case R equal to 0. Even then the formula works. So you can write R greater than or equal to 0 instead of just R greater than 0. And still the formula works. Let's see another example of that same type. Find the number of 3-letter words with or without meaning that can be formed using the letters of the word number, if repetition of letters is not allowed. Solution, and the answer of course is 6p3. Be careful, okay? You need to first of all make sure that the objects you are dealing with are all distinct. Do we have distinct letters? N, M, U, B, E, R, they are all distinct, right? So yes, now we can use NPR. So 6p3 is by definition of NPR, 6 factorial divided by 6 minus 3 factorial, or 6 factorial over 3 factorial. And then you expand 6 factorial. If you want, you can write all the way up to 1, but along the way we get at this stage 3 factorial itself. So that then you cancel with the denominator and you get 6 times 5 times 4, which is 120. Have you noticed one thing? That this formula actually does not give you any, practically no advantage actually. All you are ultimately doing is just multiplying 6, 5 and 4, which you initially also did. Instead of using this formula, if you drew those boxes, there would be 6 ways of filling in the first box. Then once that has been filled, there would be 5 ways for filling in the second box, and then 4 ways for the third box. So the formula is just, it's not giving you anything new. It's just a way of putting whatever you already know in a more fancy way. And worse still, things get mechanical. The more you use this formula, you tend to forget the source of the formula, from where it comes. So you may ultimately completely forget, if you are careless, you may ultimately completely forget that process itself by which we really find this number, that's 6 times 5 times 4. So in that sense, it's less illuminating also, but it's a formula what we can do. When we are in the pressure of writing in an exam, we don't think about those things. We just have the formula, we memorize it and we apply it. That's a bad way of doing mathematics, but that's just the way it is. But what if repetition of letters is allowed? Then what shall we do in that similar situation? Then we are back to those boxes. We can no longer use NPR because now repetition is allowed. There are 3 places to be filled in because we want 3-letter words with or without meaning. And there are 6 different letters available. So you can fill in each box in 6 ways. So in total the number is 6 cube, which is 216. And looking at this, we can also write a general result. Result means it's just an observation, but still let's write it, which is this: the number of permutations of n distinct objects taking r at a time again, but this time repetition of objects is allowed, is n to the power r, just like here you have 6 cube. And one more thing, here also can we think of r equal to 0, can we think of that case in which although repetition is allowed but you ultimately don't choose anything. That can happen in only one way, that no choice has been made, so no question of arranging things comes in the first place. And what is this number when r is 0? That is also 1. So yes, you can consider r equal to 0 even in this case where repetition is allowed. And with that, let me just end this video here itself. In the next video on permutations, we are going to see how we can arrange, how to find the number of arrangements of objects which are not all distinct.